So am I audible?
Yes, sir.
In the last lecture, Nabil, you were not there on Thursday, no?
He, yes, sir, I was absent.
So did you went through the recordings?
No, sir, I will go through it today.
Okay. So I'm just giving a very quick recap of what we did on Thursday. Thursday we started Bohr's model. So Bohr's model is valid for a single electron atom only. The example of single electron atom is hydrogen, helium plus, lithium 2 plus, beryllium 3 plus. These all are examples of single electron atom. So if you have an atom which have a single electron, at the center of the atom you have nucleus and electrons are revolving around the nucleus. That's Bohr's model. So the Bohr's model says that electrons revolves in definite orbits. The name of the orbit was shell. In shell, electron revolve with a fixed energy. Means electron neither gain nor lose energy when it is revolving in a shell. You can in chemistry you call this shell as orbit. So using a basic Bohr theory, we calculated the radius of orbit. The radius of orbit is this n square h square by 4 pi square m kz square, when n is the number of orbit or the number of shell k, l, m, n. H is the Planck constant, 4 pi is constant, m is mass of electron, k is the constant k that we use in electrostat, 1 over 4 pi epsilon naught. Z is the atomic number and E is charging it. So when you put all these values here, you get that radius of nth orbit is 0.529 n square by z. That's the first thing that we have derived. Although 90% of the numericals will use only this concept, but in few numericals, you will need this formula also. So it's better if you can remember this formula. After this, we calculated velocity. Velocity is not very important. The next is energy. So if electrons are revolving around the nucleus, they will have some energy. So electrons will have some kinetic energy. This is the expression of kinetic energy. Due to the interaction with the nucleus, electron will have potential energy. This is the expression of potential energy. And then we can calculate total energy. This relation is important, that total energy is minus of kinetic energy, which is potential energy by 2. And when we derive this thing, it comes out to be the final expression. Minus 2k square e to the power 4 pi square m z square by n square h square. So you should remember this is a very, very important relation. So in Bohr's orbit, if you know radius of the nth Bohr orbit and if you know the energy, the total energy with which electrons revolve, then you can calculate anything. Now, there are few important discussion regarding this energy. First is this negative sign. This negative sign in total energy shows that the orbit of electron is bounded orbit. Like electron cannot move out of the nucleus on its own. This electron is in a bounded orbit. It can revolve around the nucleus. This negative sign shows orbit is bounded. Negative sign shows that orbit is bounded. It is a bounded orbit. First thing. Second is it's inversely proportional to n, means if you go to higher shell, the value keeps on decreasing, and this depends upon the atomic number. Z is the atomic. So Nabil, if you want to note down something, note down these two relations. We will need this relation in today's discussion as well. Noha, you were also absent in the Thursday class, no?
Yes, sir.
You told me to keep class on Thursday and you were absent. Anyways, note these expressions, energy. We'll be using these expressions in further calculations. Now, after this, we'll draw energy level diagram. We will draw energy level diagram. energy level diagram. So energy level diagram means you are plotting energy of each orbit. So if I take, we are just calculating the value of energy in each orbit. This is what we will do. Let's first write down the energy level diagram. You can draw this energy level diagram for any atom. We'll do it for hydrogen. So this is the expression of energy. En is minus of 13.6 by n square multiplied by z square electron. For hydrogen, you can put z equal to 1. So the expression of energy will become is minus of 13.6 by n square electron. Let's draw it for individual atoms. Huh? So if I take n equal to 1, then E1 will be minus of 13.6 electron. So this is the energy of electron in the first orbit of hydrogen. You can call it as K shell, huh? Or you can call it as ground state. We call this as ground state also. You can call this as ground state or the K shell. So when you put n equal to 2, the energy of electron will become it's minus of 13.6 over 2 square. So it's 13.6 by 4. It will be minus 3.4, right? Minus 3.4 electron volt. Similarly, you can calculate for n equal to 3. So this will be, so n equal to 2 is known as first excited state. N equal to 3 is known as second excited state. And all. Now you can just draw this diagram. Huh? This is n equal to 1 level. In n equal to 1 level, energy is minus of 13.6 electron volt. Then you have n equal to 2 level. Energy is minus of 3.4 electron volt. When you take n equal to 3, energy will become minus of 1.51 electron volt. When you take n equal to 4, energy will become minus of 0.85 electron volt and so on. And at n equal to infinity, sorry, at n equal to infinity, the energy will become 0. So this is the energy level diagram. Now let's see some characteristics of energy level diagrams. So Krishna, when we are going up, like when we are going to higher energy level, what's happening with energy? Energy is increasing or it's decreasing? As we go up, like from n equal to 1 to n equal to infinite, energy is
decreasing.
increasing. It's getting less negative, right? It's increasing. So when you go to higher energy level, energy increases. First thing, energy increases. Huh? That's the first point. Second important point. If you look at the difference in energy level, like the difference in first two energy level is something like if you subtract them 13.6 and 3.4, it will get 10.2 around. Huh? And if you take difference of these two, this will be around some 1.57, 1.58. If you take difference between these two energy levels, it will be around some 0.8 something. So when you go to higher energy level, the difference between the two consecutive energy level decreases. Difference between two consecutive energy levels decreases. As you go high, it keeps on decreasing. Consecutive energy levels decreases. There's one more interesting characteristic. See, what's the minimum energy of an electron in a hydrogen atom? Noah? What's the minimum energy of an electron in a hydrogen atom? What's the minimum value of that energy? Noah, what's the minimum value of energy in a hydrogen atom? Noah is not in class. Sakina, what's the minimum value of electron in a hydrogen atom?
Minus 13.6 electron volt.
Minus 13.6. That's why we call this n equal to 1 as ground state. This is the minimum value. The next higher value is minus of 3.4. See, there is no value in between 13.6 is 3.4. That means electron will either have this energy or electron will have this energy. So electron cannot have energy in between these two energy levels. After 3.4, electron will have 1.51 electron volt. There can't be any energy which is in between. So this is known as quantization. Energy levels are quantized. Energy levels are quantized. This is known as quantization, that electron in an hydrogen atom can have only fixed values of energy. So this is what we call quantization of energy levels. After this, there's one more thing. Do you know what the spectrum means? Can anyone explain what the spectrum means?
Continuous arrangement of radiation.
Emission of radiation. See, what happens if you have an hydrogen atom, let's say this hydrogen atom. Say you have an electron which is in the excited state. When this electron will come to ground state, it will emit some energy. The energy that this electron will emit can be in the form of radiation. So it will emit some energy. That emitted energy can form a spectrum. So we have two types of spectrum. One is the emission spectrum, another is the absorption spectrum. To explain a spectrum, I'm just going back to the notes so that you know what is where in these notes. So yes, this is it, huh? Atomic spectrum. There's one example of spectrum. You have heard about Vibgyor, right? When you take a prism, you pass white light through the prism. When this light come out of the prism, it splits into 7 colors. From violet to red, you have 7 colors. This is Vibgyor. And this is the spectrum of white light. This is spectrum of white light. If you have white light, you can split this light into 7 colors. This is spectrum. So this one example of spectrum is this Vibgyor. But this Vibgyor is an example of continuous spectrum. Means when violet ends, indigo starts. When indigo ends, blue starts. When blue ends, green starts. Then yellow, then orange, and red, everything. So Vibgyor is an example of continuous spectrum. So this is not an example of line spectrum. This is a continuous spectrum. But when you take spectrum from any atom, the spectrum is not continuous. The spectrum is line spectrum. Line spectrum means you will have lines. Say you have a violet line. Then after violet line, you will have some gap, dark gap, black line. Black means there is no color. Then you will have one line. Then you will have gap. Then you will have one line. Then gap. Then one line and all. So the spectrum of all atoms, the spectrum of all elements are line spectrum. They are not continuous spectrum. Line spectrum means we'll get one colored line, then you'll have gap, then you'll have another line, then you'll have gap, then you'll have another line. So we have two types of these atomic spectrum. One is emission spectrum, another is absorption spectrum. Emission spectrum means when electrons comes from the higher energy level to the lower energy level, it emits some energy. The energy that these electrons emit will form emission spectrum. There's another type of spectrum, which is the absorption spectrum. For absorption spectrum, what we do is, let's say I take a gas. This is the gas. I take a light source. So this is a very versatile source, like it can emit all types of radiations. When this light radiation passes through this gas, what does gas do? Gas absorbs some of the wavelength. Gas absorbs some of the frequencies. Gas does not absorb all wavelength or all frequencies. Gas absorbs some particular wavelength and particular frequency. Now, why does a gas absorb some particular frequencies, not all frequencies, can be explained on the basis of energy level diagram. That's our motive. So when this passes through the gas absorbs some particular frequencies, and the frequencies which the gas absorbs is absent from the radiations. You get dark lines, some black lines. These black lines are corresponding to the frequencies which this gas absorbs. So the frequencies absorbed by the gas forms the absorption spectrum. And the emission spectrum is the frequencies emitted by the atom forms emission spectrum. And both are line spectrum, means these spectrums are not continuous. This spectrum will have break. You will have one line in emission spectrum, you will have one colored line, then gap, then another colored line, then gap, then another colored line, and then gap. While in absorption spectrum, you will have black lines. You will have dark lines, then some color, then dark line, then some color, then dark line, then some color. So these are line spectrums. And the interesting thing is, line spectrum of every element is unique. Line spectrum, emission or absorption, both. Of spectrum of all elements are unique. Like emission spectrum of not two elements could be same, just like the fingerprints of humans. Fingerprints of two humans cannot be same. Just like this, the line spectrum of two elements cannot be same. Every element have its unique line spectrum. This is how we sometimes identify elements in the astronomical structure. Like if you have a star, some light is coming from the star, and just by analyzing that light, you can say, okay, what are the elements present in that star? So what we do, the light coming from the star, we split that light. We study the emission spectrum of that light. And just by studying the emission spectrum, you can decide, okay, if it is matching with iron, that means iron is present on that star. If it is matching with copper, that means copper is present over the star. So spectrum. So is it clear? The absorption spectrum and emission spectrum? Nabil, Ishma, Arpit. So, Noha, can you explain why we have colored lines in an emission spectrum? What does colored lines in an emission spectrum represent? Yes, Noha. Noha, what does colored line in an emission spectrum represents? Sakina Abbas, what does colored lines in emission spectrum represents? Hishma, what does colored lines in an emission spectrum represent?
The frequencies that are not absorbed.
Not absorbed, or the frequencies that are emitted? I'm asking about the emission spectrum, not the absorption. In emission spectrum, gas emits some frequencies. So the colored lines represent those frequencies which are emitted by the gas. So, Nabil, what does dark lines in absorption spectrum represents? Nabil, what does dark lines in absorption spectrum explain? Can anyone answer what does dark lines in the absorption spectrum represents?
It is a frequency absorbed by the spectrum.
Yeah, this represents the frequency absorbed by the gas. And see, if you try to explain this thing on the basis of energy level diagram, when a gas absorb any frequency, it jumps to the higher energy level. The electrons jumps to the higher energy level. When a gas emit energy, the electrons comes to the lower energy level and they emit some energy. So the next question is, can a gas absorb every possible energy? Like if I take this hydrogen atom and if I give this hydrogen atom an energy of, let's say, 13 electron volt, can this hydrogen atom absorb 13 electron volt? Let's see. In ground state, the energy of hydrogen atom is minus of 13.6 electron volt. And if you give it some 30 electron volt, the energy will become minus of 3.6 electron volt. There is no energy level corresponding to 3.6 electron volt. After 13.6, you have 3.4, then you have 1.51. You don't have any energy level corresponding to 30.6 electron volt. This simply means your hydrogen atom will not absorb this energy. An atom cannot absorb all energies. Similarly, an atom cannot emit all energies. An atom can absorb or emit only those energies which are corresponding to the difference in energy levels. So the minimum energy that your hydrogen atom can absorb is this 12.2 electron volt. Will absorb this energy and will jump to 3.4 electron volt. So that should be very, very clear. Like the only thing which is which have some good weightage in atom is this logic that an atom cannot absorb every energy. This is the meaning of quantization. An atom cannot emit every possible energy. An atom can absorb only those energies which are corresponding to the difference in energy levels, and it can emit the same energy. That's why the spectrum is not continuous. The spectrum is line spectrum. Atom emit particular energies. It absorb particular energies. Is it clear, this discussion, Arpit, Alia, Anshika?
Yes, sir.
This is something very, very important. Why the spectrum is a line spectrum? So I will dictate now. You have to write something. Just note it down. Note down these things. Then it's got it. If you can understand this thing, why atom does not absorb all energies and why atom does not emit all energies, that means atom is over. Just note it down, please. Tell me once you have written. I will dictate 2 more points. Yes, written. Can I dictate further to further next point? Anshika, Nabil, Noha. Written up to here?
Yes, sir, done.
Okay. So write down the next point. Next point, point number 4. So write down. An atom can absorb or emit. An atom can absorb or emit only those energies. An atom can absorb or emit only those energies. In the bracket, you can write frequencies. So energy and frequency are related. E is equal to h nu or hc by lambda. In the bracket, you can write frequencies, which are corresponding to the difference in its energy level, which are corresponding to the difference in its energy level. So it can absorb only those energies or those frequencies which are corresponding to the differences energy level. That's why spectrum is a line spectrum. That's why spectrum is a line spectrum. You don't have continuous spectrums, you have line spectrums. That's why spectrum is a line spectrum. Okay, after this, let's do some questions, some basic questions on this. Hmm. Do this question number 13, not 13, don't do 13. 14, first part of 14. First part of question number 14. Note down the question. Gautam, Sakina, written? Have you written the question?
Writing, sir.
Just write first part. Don't write second part. This we will do in when we study series, spectral series. Just write the first part.
Sir, we get
Sorry. See, in question number 14, first part, you have to show that an electron in an hydrogen atom cannot have this energy. So to show this thing, what you can do is, this is the expression of energy, right? Minus of 13.6 by n square. You put the value of this energy and try to calculate the value of n. If value of n comes out to be an integer, that means this energy is possible. But if value of n comes out to be a decimal or a fraction, that means this value is not possible. So if I write E to be minus of 6.8, which is equal to minus of 13.6 by n square. So this minus minus gets cancelled out. You can write that your n square is 13.6 by 6.8. Obviously, it's not an integer. N is not an integer, which simply means it can't absorb this energy. This energy cannot, or hydrogen atom cannot have this energy. Electron in a hydrogen atom cannot have an energy which is minus of 6.8. Right, Nabil? Clear? Anshika, Alia, Arpit? Just get the value of n. If the value of n is an integer, that means that energy is possible. But if the value of n is not an integer, that means the energy is not possible. Now let's solve this part, the first part of question number 13. Just note down the question, please. Note down the first question. Okay, just solve the first part and write your answer in chat room. You need kinetic energy of electron in the second excited state and third excited state. Arpit, what does second excited state means? What's the value of n for second excited state? Arpit. Anshika, what's the value of n for second excited state? Right, Alia. Noah, value of n for second excited state?
So 3.
3. So in the n equal to 3 state, you just have to calculate the value of n or the value of total energy. There's a relation between kinetic energy and total energy. We have derived that kinetic energy is just negative of total energy. So if you can calculate total energy, you know kinetic energy. So did you write the question? Question number 3? Everyone. Hishma, did you write the question? The first part only.
Yes, sir.
So for the first part, question number 13. This is the formula for hydrogen atom. Minus of 13.6 by n square. So it's asking in second excited state. Second excited state means n is equal to 3. When you put n equal to 3, you get E3 is minus of 13.6 by 3 square. So when you divide it, it comes out to be minus of 1.51 electron volt. But see, this is the total energy. It's not asking about the total energy, just asking about the kinetic energy. The kinetic energy is just negative of this, which is 1.51 electron. This is the kinetic. Similarly, you need kinetic energy in third excited state. For the third excited state, your n is equal to 4. So you can similarly get the value of E for the negative of this will be the kinetic energy. Note it down. The same calculation. After this, do question number 24. This is again an important question. Question number 24. 24. An important question. Write down question number 4. This is very, very important. So which transition will correspond to this 620 nm? So did you write the question, Hishma, Noha, Shakina, Nabil? This 24. Just don't do it fast, fast, fast. Very good, Noah. See, to solve these type of questions, so what does question says? This is some atom. Which of the following transitions will result in emission of photon of wavelength 620 nm? So the emitted wavelength here is 620 nanometer. So for this 620 nanometer, do one thing. First, calculate your energy. This radiation is emitted by your atom. So calculate energy corresponding to this wavelength. So the energy corresponding to this wavelength is simply hc by lambda. It would be better if you can convert this lambda in angstrom, and angstrom this will be 6200 angstrom. Just put all values. hc is 12400. Lambda is 6200. So this and this will get cancelled out. So it comes out to be 2 electron. So the energy corresponding to this wavelength is 2 electron. So the transition in which energy difference is 2 electron volt will emit this wavelength. So if you look, see the first transition, A, it's 0 to -1. The energy difference is 1. It can't be possible. B, 0 to 3. The energy difference is 3, but you need 2. Not possible. C, not possible. D, 1 to 3. The energy difference is 2. This is possible. So the correct transition is transition D. Is it clear? Gautam,
Yes, sir.
Naveel? No, no. It's a very bold question. No, no, no. So this is the transition D. Okay. These were the questions of atomic structure. Oh, important questions. There are a few more things. Then next is the ionization energy or excitation energy. There are two terms. One is excitation energy and potential. So excitation energy simply means if you have an electron in some lower energy level and you want to send this electron to a higher energy level. Here the energy is E1. In the higher energy level, the energy is E2. So excitation energy simply means this energy difference, E2 minus the energy required to send electron from some lower energy level to higher energy level is the excitation energy, delta E. That's it. For potential, what you can do is you can write your energy in this way, it's EV. We use this relation in photoelectric effect also. Energy is charge multiplied by potential. So your energy is charge, which is E multiplied by the potential. So delta E is E. So this V is the excitation potential. V is the excitation. So this relate energy and your potential. This is excitation energy and excitation. Similarly, you can define two more terms. One is ionization energy and ionization potential. What does ionization means? Arpit. I think Arpit and Anshika are not in this. Arpit, what does ionization means? Anshika, what does ionization means? Sakina Abbas, what does ionization
Sir,
means?
ionization is the like energy required to fully take out one or like more than one electrons from the shell.
Ionization means taking electron out of the atom. Or in terms of energy level diagram, you can say taking your electron from n equal to 1 level to n equal to infinity is ionization. So in n equal to 1 level, let's say energy is E1. In n equal to infinite level, energy is 0. So you can say that ionization energy is Z2 minus or E infinity minus E. This is ionization energy. Energy required to take electron from n equal to 1 level to infinity. E infinity minus E. E infinity is 0, so it's just minus. This is how you can calculate ionization energy. If you want to calculate ionization potential, then simply compare it with EV. This V will be your ionization potential. So there is no formula for calculating excitation energy or ionization energy. It's just simply the difference in energy level. You should know these terms. Ionization energy means taking your electron from some energy level to n equal to infinite. So this is your ionization energy potential. Please note it down. We'll do spectral series now. Written up to here. Ishma, Sakina.
Yes, sir.
Yes,
So,
sir.
okay, the last part of atomic structure is spectral series of spectral series of So, Sakina Bas, when does an atom emit radiation? So, if I take an atom, when it will emit some radiation, in which type of transition it will emit radiation?
Sir, when
Yes, when?
because of the spectrum,
Yes, when does an atom emit some energy, emit some radiation? When it jump from low energy level to higher energy level, or when it jump from high energy level to low energy?
when it jumps from lower to higher.
When it jump from lower to higher, uh, Hishma, when does electron emit radiation?
When it goes from higher energy level to low energy.
Yeah, when it goes from high to low. When it goes from low to high, then it absorb energy. It emit energy only when it comes from higher to lower, from higher to lower energy. So spectral series of hydrogen means you are deriving some relations for the emission spectrum of hydrogen. So when electrons jump from higher to lower energy level, they emit some energy. So you get some pattern. Basically, what happens is the spectral lines forms groups. So when electrons jump from higher to lower energy level of hydrogen, then you get spectral series, emission spectrum. These lines form certain groups. These groups are known as spectral series. So let's first learn how to calculate the wavelength of these series. So let's say you have electron in N2 level, then it jumped to N1 level. Here its energy is E2, here its energy is E. When it jumps from high to lower energy level, it emits some energy. So the emitted energy will be E2 higher energy minus lower. So you can write that your delta E is E2 we will write from this expression, this complete expression, this minus 2k square e to the power 4 pi square m minus 2k square e to the power 4 m pi square m z square m square square pi square n square z square h square. Please check. This was the expression. Is this correct expression? This is into minus, then you need minus of e. So this will be minus of 2k square e to the power 4 m pi square z square by n1 square h square. From these two equations, you can take some terms common. Instead of n2, everything is same. So I can take this 2k square e to the power 4 m pi square z square by h square. When you take these terms as common, you are left with just 1 by n. See, minus minus will give plus. So I'm writing this first and this second. Minus 1 by n2 square. I want to calculate wavelength. So delta E, I can write hc by lambda is 2k square e to the power 4m pi square z square by h square 1 by n1 square minus 1 by n2 square. I need 1 by lambda. So I can write this as 1 by lambda is, you can take this in denominator. So it will be 2k square e to the power 4 m pi square z square is h cube c. It's 1 by n1 square minus 1 by n2 square. See, instead of z, each and every term is fixed. So you can write this as 1 by lambda is Rydberg constant into z square, 1 by n1 square minus 1 by n2 square. This is the expression. So 1 by lambda is RH z square, 1 by n1 square minus 1 by n2 square. RH is known as Rydberg constant. The value of Rydberg constant is 1.10 raised power 7 meter. So we can calculate, if you want to calculate exactly for hydrogen, when you take hydrogen, the Z comes out to be. So when you put Z equal to 1, so we have 1 by lambda is RH, 1 by N1 square is 1 by N2 square. This is the relation. 1 by lambda is Rydberg constant, 1 by N1 square minus 1 by N2 square. Please note it down. From this, we can form series like Lyman series, Balmer, Pasha, bracket fund. We can form all series. Yes, everyone have written up to here? Okay. So this is the formula that we'll be using. Let's start with this is the formula that. Okay, note down up to here. Then we'll calculate different series like Lyman, Balmer, Paschen, Brackett, and Fund series. Okay, let's start with the first series. The first series is the Lyman series. Anshika, in this expression, which one is the lower energy level and which one is the higher energy level? Vishma, in this expression, which one is the lower energy level and which one is the higher energy level?
Sir, N1 is the lower one and N2 is the higher one.
So in Lyman series, N2 could be any level, but we fixed N1 to be equal to 1. So your N2 could be 2, it could be 3, it could be 4 and all. But N1 is first energy level. This is the Lyman series. So we fix the value of lower energy level. So if you fix the value of lower energy level to N1 equal to 1, the series is Lyman series. In Lyman series, you can write this as 1 by lambda is RH 1 by 1 square minus 1 by N2 square. Lyman series lie in the ultraviolet region. It lies in the ultraviolet region. Now, there are a few questions like calculate the maximum wavelength of the Lyman series and the minimum wavelength of maximum. So for maximum wavelength, what you can do is, see, energy is inversely proportional to wavelength. So if energy difference is minimum, that means wavelength will be maximum. So the minimum energy difference will be the transition from 2 to 1, because after 1, the nearest is 2. So if you put N2 equal to 2, then your energy difference is minimum, but the wavelength will be maximum. You can write this as 1 by max is RH 1 by 1 square minus 1 by 2 square. So you can write this as 1 by lambda max is RH. It's 1 minus 1 by 4. So you can write this as 1 by lambda max is RH. 1 minus 1 by 4 means is 3 by 4. So you can write that lambda max will be 4 by 3 RH. This is the maximum wave. Similarly, if you want to calculate the minimum wave, so again, lambda and E are inversely proportional. Can you guess, Nabil, what will be the transition for the minimum wavelength? Nabil Ahmed. What will be the transition for the minimum wavelength? So the transition corresponding to maximum wavelength is 2 to 1. What is the transition for the minimum wavelength? Nabil. Nabil, you're not audible here. Krishna. Transition for the minimum wavelength. The transition where energy difference is maximum. So
So 1
energy,
to 2.
no, 1 to 2, in 1 to 2, energy difference is minimum. The 2 to 1 is the first transition. What is the
Okay, 1
last
to
transition?
infinity.
Yeah, infinity to 1. This.
Yeah.
So this 2 to 1 is the transition that is corresponding to maximum wavelength. For minimum wavelength, this is 1 by lambda minimum is Rydberg constant 1 by 1 square, 1 by infinity square. So it comes out to be 0. So lambda minimum will be 1 by RH, and here also your RH is in denominator. So for every series, you have to remember the value of N1, the values of N2, the region in which that transition lies, condition for the maximum wavelength. Always the first transition is the maximum one. Then the minimum. It's always infinity to the lower energy level will be the minimum one. Note it down, then we'll do other different series. Note it down, please. So for each and every transition, just have to remember the value of N1, the spectrum in which it lies, the condition for maximum and minimum wavelength. That's it. And also, there's one more thing. Okay, let's note it down. Can I scroll it now? If you have written up to here, Vishma, Gautam.
Yes, sir.
Okay, now there are fixed names of the transition also. Like the first transition of every series, first transition is known as alpha. Second transition is known as beta. Third transition is known as gamma. If you take the case of the Lyman series, first transition means 2 to 1. Second transition means 3 to 1. Third transition means 4 to 1. So instead of saying 2 to 1, you can say alpha or beta or gamma. You should remember this. Just note it down. Put down these codes. And this is valid not just for Lyman but for all series. First is alpha, second is beta, third is gamma. Okay, after Lyman, the next is Balmer series. For Balmer series, you fixed N1 equal to 2, lower energy state is 1, 2. N2 could be 3, it could be 4, it could be 5, up to infinity. For maximum wavelength, the transition is 3 to 2. For minimum wavelength, the transition is infinity to 2. And this lies in the visible spectrum. After Balmer, you have Paschen. In Paschen, N1 is 3, N2 is 4, 5 and all. For maximum wavelength, the transition is 4 to 3. For minimum wavelength, the transition is infinity to 3. And this lies in infrared region, IR. IR. Then you have bracket. In bracket, your N1 is 4, your N2 is 5, 6, 7 and all. The maximum wavelength is corresponding to this transition, 5 to 4. The minimum wavelength is corresponding to this transition, infinity to 4. This also lies in infrared region. IR means infrared region. After bracket, you have last, which is Fund series. And 1 is equal to 5, and 2 is 6, 7, up to infinite. For maximum transition, for maximum wavelength, the transition is 6 to 5. For minimum wavelength, the transition is infinity to 5, and this also lies in the IR region. Note it down, please.
Yes, written. So that was the last topic of atom. After atom, this topic, there is failure of Bohr model that you will read on your own. I have mentioned in the notes also. Failure of Bohr's model. So in the next class, this is over. The next class will start with nucleus. Nucleus is a small topic. On Wednesday, we'll try to finish this nucleus.